Hello students, welcome to Smile with Chemistry. Let's discuss about the Werner's coordination theory. Werner, the father of coordination chemistry, put forward his famous theory of coordination to explain the formation and structure of complex compound. According to this theory, the valency of central atom does not remain necessarily confined to a fixed small number as expected in classical idea, but it may get extended over the entire surface of the atom, and these valencies are of different strengths. The basic postulates of this theory are as follows. A metal in a coordination compound possesses two types of valencies, that is, the primary valency, which is otherwise known as the principal valency, and second one is the secondary valency, which is otherwise known as the auxiliary or residual valency. Primary valency corresponds to its oxidation state and secondary valency corresponds to its coordination number. Primary valency is ionizable and is non-directional, whereas secondary valency is non-ionizable and is directional. Every metal atom has a fixed number of secondary valency, that is, it has a fixed number of coordination number. The primary valency is utilized to form the ionic bonds, while the secondary valency is utilized to form the coordinate covalent bond in space. The metal atom tends to satisfy both its primary valency as well as its secondary valencies. Primary valencies are satisfied by negative ions, whereas the secondary valencies are satisfied either by negative ions or by neutral molecules. The directional property of the secondary valency gives a definite geometrical shape of the coordination sphere. It also determines the stereochemistry of the complex. According to this theory, we can predict the exact formula of the complex compound. With the help of this theory, Werner explained the structure of various complexes formed by COCl3 and NH3. He estimated the number of ionizable chloride ions in each complex by precipitation with an aqueous solution of AgNO3. The primary valencies are represented by dotted lines and the secondary valencies are represented by solid lines. With these examples, we may able to know the structure of the complex. Let's discuss the examples. The first example is COCl3.6NH3. Look at the structure. This complex, cobalt has primary valency 3 and secondary valency 6. When COCl3.6NH3 dissociates, it gives CO.6NH3 3+ complex and 3Cl- ions. This 3Cl- ion again reacts with 3 Ag+
Therefore,
ions
all
to
the
give
secondary valencies
3
of
molecules
cobalt
of
are
HCl,
satisfied by 6
which is a
ammonia
white
molecules
precipitate.
and 3 chloride ions
This complex
satisfy the
gives
3
white
primary
precipitate
valencies.
with an aqueous solution of
Thus, the structure
AgNO3,
of the complex
which indicates
may be
the
written
presence
as
of ionizable chlorine.
NH36Cl3.
Then look at the second example, COCl3.5NH3. Look the structure. Here, COCl3.5NH3 when dissociates, it gives COCl.5NH3 2+ complex and 2Cl- ion. Then this 2Cl- ion reacts with 2 Ag+ ion to give 2 molecules of AgCl, which is also a white precipitate. The precipitation of only 2 chloride ions indicates that 2 chloride ions are outside the coordination sphere and the remaining 1 chloride ion and 5 NH3 molecule are present inside the coordination sphere. So, in this complex, out of the 6 secondary valencies, 5 are satisfied by 5 ammonia molecules and the rest 1 is satisfied by chloride ion. This chloride ion also satisfies the primary valency of cobalt ion. The other 2 chloride ion satisfy the primary valencies of cobalt ion. Thus, the structure of the complex may be written as CONH3 5Cl Cl2. Look at the example number 3, COCl3.4NH3. See the structure. When COCl3.4NH3 dissociates, it gives COCl2.4NH3 plus complex and Cl- ion. Then Ag+ and Cl- gives rise to AgCl white precipitate. This complex gives white precipitate with AgNO3 solution indicating the presence of the ionizable chlorine. It is estimated that one molecule of the complex contains 1 chloride ion. Therefore, in this complex, out of the 6 secondary valencies of cobalt, 4 valencies are satisfied by 4 ammonia molecules and the remaining 2 secondary valencies are satisfied by 2 chloride ions. These 2 chloride ions also satisfy the 2 primary valencies of the cobalt ion and the remaining one primary valency of cobalt is satisfied by the third chloride ion. Thus, the structure of the complex can be written as CONH3 whole 4 Cl2 Cl. The last example, COCl3.3NH3. See this structure carefully. This complex does not give any precipitate with AgNO3 solution, and thus it does not have any ionizable chlorine. Therefore, in this complex, 6 secondary valencies are satisfied by 3 ammonia molecules and 3 chloride ions. These 3 chloride ions also satisfy the 3 primary valencies of the cobalt ion. Thus, the structure of the complex can be written as CONH3 whole 3 Cl3. So, comparing these 4 examples, you can relate the structure of the complexes. These are the applications of Werner's theory. It is helpful in predicting the exact formula of the complex compound. It also predicts the different geometry of different complexes having coordination number 4 or 6. It can explain the existence of isomerism in coordination compounds. And these are the drawbacks of Werner's theory. It could not explain the certain properties of complex compounds such as color, magnetic behavior, etc. And it could not explain why the coordination sphere has a definite geometry. In this video, we have covered the basic postulates of the Werner's theory and the explanation of the theory and structure of the complex with the help of 4 examples, then the applications of Werner's theory and drawbacks of Werner's theory. Thanks for watching this video, and don't forget to like, share and subscribe this channel.